Hello friends, my name is Tushar and today I'm going to talk about how to design a distributed database. Designing a distributed database is a very hard problem, and today I'm going to go over a high or level overview of some of the different things happening in the database, and I hope that the readers will go back and read in details about those topics. So what we're going to do today is go through a list of topics one by one, and then hopefully that will help you understand how you could design a database which can scale as more user data is added or more I/O is added to the system. So first we'll talk about the characteristics of the database. So the database we're going to design today is going to be more highly consistent rather than highly available. So this is different from a database like, say, Cassandra, which relies a lot on eventual consistency and stresses for higher availability rather than consistency. The next thing we are going to do is look at the basic operations which the database can support. Then we look at the overall architecture of the database. Then we'll talk about the metadata manager, where we'll talk where and how the data is, the metadata of the database is stored. Then we'll go into the replication group. This is where all the interesting stuff happens. Then we'll talk about the data plane, the control plane, and then we'll look at some of the interesting edge cases and talk how we solve them. And finally, we'll talk about the numbers or how much this database can scale given certain conditions. So next, let's jump into the characteristics of the database. When designing a database, these characteristics have to be considered in this order. So durability is the most important characteristics for a database. If you lose customer data, you would not be in the business of database system. The next important thing is availability over performance. So you would rather return data in a slow manner than not returning data at all. And finally, we should consider the performance characteristics for the database. One thing which we are not going to talk about here today is security, and it is again a very important thing, but we are not going to cover that in this video, and we'll assume that client will do their own encryption before sending data to our database system. Next, let's talk about consistency model. So the database which we are going to design today is going to have strongly consistent property. What does strongly consistent means? It means that the read after the most recent successful write will always see the results of that write. And then our database is not going to support ACID properties. For example, there will be no atomicity in the database. So you cannot send like 5 requests to a database and assume that all of them should be executed together or none should be executed. Or there will be no isolation. So there will be no locking at a table level or low level or row level whatsoever. So next, let's talk about the basic operations which our database is going to allow. Our database is going to consist of a bunch of tables, and each table will have a very simple key and value record. With every key value record, we are also going to store a sequencer, and I'm going to talk about sequencer a little bit later on. So these are the operations you can perform on the database. Creating a table, putting a key and value in a given table, getting a key in a given table and getting its value, deleting a key in a given table, listing the keys in a table in a sorted form. So the list operation will return you all the keys in a sorted manner along with their values in a given table. And finally, delete table, and this is an optional operation which we are not going to implement, but if we can implement all this, they should be fairly trivial. With every record, with every key value pair in a table, we are going to store a sequencer which is going to be increasing and unique number. To get this unique number, we are going to have a sequencer which is going to be made up of these 3 paths. The first path is a timestamp in nanoseconds, which will take 8 bytes. Then we have a unique number per node, which will be 4 bytes. And this number will keep, as soon as it reaches the end of the 4 byte, it will again circle back from 0 and start again. And then we'll have a unique node ID, which will again be 4 bytes. So since we have 4 bytes for a node ID, in total we can have 2 raised to 32 nodes, which is about 4 billion number, which is more than enough for our use case. So a total of 16 bytes sequencer will be stored with every key value record, and then this sequencer will be increasing and unique. And why we're going to use this sequencer, I'm going to talk a little bit later on. So next, let's take an example and apply some of these operations on that Example. We create a table named stock and it has a keys name and values price. And as I said before, every record will have a sequencer by default, so I'll also have a sequencer here. The first operation I do is a put, and I say in stocks put B and price 100, and let's call it sequence number 1. Then I'll do a put again, and this time the price, the name of the stock is A. Since we are sorting by the key, A will logically come before B in our table, and 120, and sequence number 2. And this sequence number 2 will be higher than sequence number 1 because our sequence is unique and always increasing. And then I do a third put C, so C, and then this is 135, and then the sequence number will be, let's call it sequence 3. Sequence 3. Okay. And if someone does a get on A, then he should get 120 back. And if someone does the list operation of the stocks, we should return this A, B, C in a sorted form along with their values. If the number of records in a given table is really, really big, it's a large number of records, then we can also implement some sort of pagination to return some number of records at a time. So let's talk about why we need the sequencer. Let's suppose we got this put D and 140, and then another put D at 160. Let's suppose client did this 2 puts on this stock D at about same time. Remember, this is a distributed system, and also we are not providing any locking and all those business. So if client does 2 puts at about same time, then we are going to use sequence number to find out which of the put wins. So for us, the last write or the last put wins, and to figure out which one is the last put, we're going to use sequencer. So both these puts will come to our system, both of them will be stored somewhere in the database, and then finally, when the reconciliation happens, we'll find out that who has a higher sequence number and whoever has the higher sequence number will win. And that's where this sequencer is going to be used. So after seeing this example, next let's look at the overall architecture of our distributed database system. This is the overall picture of what our distributed database system looks like. We'll assume that all these components are running inside a data center. And if you want protection at a data center level, then you can split this across multiple DCs. But once you do that, then you have a cross DC talk, which can have performance implications. So at the front end of our distributed database system is a load balancer. The load balancer receives a request, then sends it to one of the request managers. The request manager consults the metadata manager to figure out who owns the table and that part of the table. And then request manager, after consulting with the metadata manager, sends a request to one of the replication groups who is the owner of that part of the table. Replication group consists of 3 or 5 nodes for redundancy purposes, and in each replication group we have one leader. Request manager will talk to that leader and will do the get or the put or the list operation. And then we have this controller. This controller is keeping an eye on all these replication groups, and if any of them become too hot because the table is getting very big or some other factor, then what controller is going to do is going to start splitting that table into smaller tables and start spreading them over multiple replication groups. And although I have drawn different boxes here, it's possible that one actual physical host could be playing multiple roles. It could be a request manager, it could also be a replication group owner, it could be a metadata manager. So this is the overall high-level view. Next, let's start digging into more details about metadata manager and this replication group. Metadata manager is going to hold small amount of data which has to be highly consistent and which has lots of reads and fewer writes. Let's look at some of the bullet points for the metadata manager. The first responsibility of metadata manager is to do a leader election in a replication group. We're going to talk about replication group next, but what it is a bunch of redundant nodes, and one node among those nodes is a leader. and it's metadata manager's responsibility to do that leader election, and it's its responsibility to figure out in a given replication group who the leader is. The second responsibility for metadata manager is to keep the mapping of table part to replication group. Coming back to our stocks example, let's suppose that this stocks table has billions of records. So we want to split this stocks table into smaller parts and have different replication group for each part. So for an example, stocks from A to C, not including C, would go to replication group 1, and then stocks from C to L, not including L, will go to replication group 2, and stocks from L till the end of the stocks, and we use a special symbol for that, will go to replication group 3. And in the future, I'm going to talk about how you split and unsplit these tables in the control plane job. But for now, all we know is that metadata manager keeps a track of the table and parts of the table to the replication group. There are a bunch of options for using metadata manager. For example, you could use Zookeeper, you could use HD, or even you could use Redis. If you're going to be too adventurous, and I bet a lot of companies do, you could write your own Paxos or Reft algorithm. These are nothing but consensus deriving algorithms. These two are pretty heavy duty topics, and I'm not going to talk a lot about them in this video because frankly speaking, they deserve videos of their own. So data stored in the metadata manager is not always going to be consistent because of network split. So we'll add more protections at the replication group level so that we are not in an incorrect state. Also, we try to keep all data in memory. All the data of metadata manager, we want to keep that in memory of the request manager, so that request manager does not have to talk to metadata manager for every request, but instead it can consult in-memory data and talk directly to the replication group. And if the data on the metadata manager changes, then it can propagate that information to all the request managers, and they can change their in-memory view. And finally, the data stored by metadata manager is extremely critical, so we need to back it up as frequently as possible, possibly whenever the state of the metadata manager changes. So this is a brief overview of what metadata manager is, and as we talk through into this video, you will realize how and where we're going to use metadata manager. So next, let's talk about replication groups. The replication group consists of a bunch of nodes, preferably an odd number of nodes, so that it's easy to do majority or quorum. In this case, let's assume we have 3 node replication group, which means that every record will be stored in 3 different replicas, and at max we can lose 2 replicas and still have the data. If you want more redundancy, then you can have 5 node replication group. Inside every replication group, there will be one and only one leader, and every request, every get, every put, every delete, and every list will go through that leader. And that's why our system is strongly consistent, because every replication group has one leader and every request is going to go through that leader. So we have one leader and 2 followers, and these followers try to stay in sync with this leader. Whenever a put happens, we make sure that majority of nodes, including the leader, always apply this put before we respond OK to the user. And in this way, if a leader ever went down, then there is at least one other host which has the exact same data, and then that node can take the position of the leader. So what's inside the node? As I said before, we are not going to focus too much about that, but let's quickly look at what's inside a node. It has basically 2 big parts. One is append only log. So there is a log in which we are appending data in a hard drive, and the reason we use that is because sequential writes are extremely cheap. So whenever put comes in, the first thing we do is we append it to the append only log, and then for indexing purposes, we use B+3 or LSM tree. And since the data is securely stored in a hard drive in an append only log, we can keep some data in memory and do not have to flush our B plus tree or LSM tree straight into the hard drive. So as I said, indexing can be done by B plus tree or LSM tree. If you have a read heavy system, then you would use a B plus tree. For a write heavy system, you would use an LSM tree. Most of the newer databases, most of the newer distributed databases seem to be preferring LSM tree over B plus tree. So when a put comes in, it'll first go to the leader. Leader will apply that put to its append only log, and at the same time will send the message to both the followers, and then the followers will try to apply that put into their append only log, and as soon as one of the followers respond back to the leader, and as soon as the leader is done applying the data in its own log, it will reply OK to the user, because majority of the nodes, including the leader, has the data, and in case the leader went down, that other node can take its position. So this is how our replication group will work. There are many error conditions which can happen, like you can have a split leader where two nodes think that there could be leader, and I'll talk about these error conditions later on in the video. So let's take this small example where we have 4 tables. Table 1 has 2 parts, part 1 and part 2, because it's a really big table, and part 1 is stored in replication group 1 and part 2 is stored in replication group 2. Then table 2, 3 and 4 are small enough table that they can be stored in a single replication group. So table 2 and 3 are stored in replication group 1 and table 4 is stored in replication group 2. So this is my introduction to replication group. Next, let's talk about data plane. We are back to our big picture diagram, and let's apply some operations and see how the data request plane path will work. So we have stocks table, which is really big, so we have split it into 2 replication group. A to L, not excluding L, is in replication group 1, and L till the end is in replication group 2. So let's suppose operation we get is put into stocks table key G and value 100. So request comes via load balancer to one of the request manager. Let's suppose this guy got it. Then it consults its in-memory view, which should have this data, and if it does not, then it can talk to the metadata manager. It will see that G should be in this particular replication group 1, because everything from A to L is in replication group 1. So it will talk, then it will go and check who is the leader of replication group 1. Again, that data is in-memory version, and it will find out that A is that node. So request manager will then talk to A and will say that, hey buddy, put G with value 100 into its database. Request manager will also generate the sequencer, and remember we are using sequencer for resolving any disputes. So it will send G 100 and a sequencer to A. What A is going to do is it's going to apply this data into its append only log and eventually into its B plus tree or LSM tree, and will tell both the nodes to apply it in their hard drives. And if one of them says okay, they have applied, then, and if once A is done applying, then it will reply okay to the request manager, and then request manager via load balancer will reply okay to the end user. Similarly, if a put stocks Y100 comes, then request will come to the request manager, this guy. It will consult into its metadata manager view that who is the owner of Y, and that is replication group 2, and then it will see who is the leader of replication group 2, and that's D. And then this guy will talk to this replication group, and here again this leader will apply this data to its own hard drive and make sure one or both the followers apply in their hard drive, and once that is done, we return the data back to the request. We return OK to the request manager, and he'll reply back OK. When you do a get, again the request will come to one of the request manager. It will see where Y is. Y is in this range. It will talk to replication group 2. The request will go through the same leader, so it will get the most consistent view. It will get the data back, and request manager will reply back. And if it did a list operation, the list will come to one of the request manager. This request manager knows that this table is split into 2 parts. So first it will start scanning data from here, and start streaming that data back to the user. And once that data is done streaming, then it'll start streaming data from this part, which is replication group 2, and then it'll start streaming that data. If the list operation takes a lot of time, we could split into multiple requests where we could only fetch like 500 requests and then return it back and say that, hey, the next request starts from this particular key, and then client sends that key back, and then the request manager starts that request from that particular key, and so on. So this is how the request plane, this is how the data plane works. A lot of things can again go wrong, and in this picture, in this view, and we'll talk about them when we talk about error situations. So next, let's talk about control plane, where if a table gets really hot or really big, how do we split them into multiple parts? First control plane job is leader management. When a new replication group comes in, all the 3 nodes in a replication group try to become a leader, and based off a consensus protocol like Paxos, metadata manager will elect one of them as a leader, and then all the reads and writes for that replication group will go through that leader. All the nodes in the replication group are constantly heartbeating with the metadata manager, and that's how metadata manager knows that the nodes are still alive. If for any reason leader stops heartbeating with the metadata manager for a certain amount of time, let's say 1 second, then the metadata manager is going to assume that the leader is lost, and then it will try to elect a new leader. We know that at least one, and in the good scenarios, both the nodes should be caught up with the leader. So all the caught up nodes can take part in the leader election, and one of them will then become the new leader. There are 2 problems which happen here. First is, in the new leader election, there is a scenario where the old leader could still be alive and a new leader is there. So we have what we call split brains, and we're going to talk about later in the video how we handle that. The second thing which can happen is there could be up to a second where a replication group is unavailable, so all the reads writes for that replication group won't work. So this is a situation where we are preferring strong consistency over availability. If you think about CAP theorem, we can achieve either consistency or availability given partition tolerance, and in this database we are preferring consistency over availability. This is different from other databases like Cassandra, where you could pick availability over consistency. Second control plane job happens when follower starts falling behind the leader. So let's suppose in this replication group we have this leader, and we know that there is at least one node who is in complete sync with the leader, and let's suppose that the other node is falling way behind the leader. It's not able to stay in sync with the leader. And let's suppose the reason for that is some malfunctioning hardware on that node. So the controller who is sitting there is monitoring all the replication groups, and it realizes that this one node is not able to stay in sync with the leader. So what it does is it takes there's a pool of available nodes, it takes one of those nodes and replaces that into this replication group, updates the metadata manager, and makes sure that that node stays in sync with the leader, and then flags this node for further inspection. Third and the most complicated control plane job is splitting hot tables. What is a hot table? Hot table is a table which is growing in size, which is growing really big in size, or the number of IOPS, input output, on that table is very high. When that happens, when a table becomes hot, our application group might not be able to handle that table. So the controller guy here is sitting and monitoring all the replication groups to see that the number of IOPS or the size of the replication group is in control size. And if that's not the case, then controller finds out that what table is responsible for replication group to become really big. Then let's suppose that in our scenario, stocks is a table which is growing really big. So right now, stocks, all the entire range of stocks table is in replication group 1, but it has gotten really big. So first thing controller will do is figure out at what point it should split this table, and it'll apply some heuristics to see what is the right point. We do not want to split the table in the middle, because that will involve a lot of work about copying, and that might turn out to be counterproductive. So controller will find an appropriate point to split this talks table. Let's suppose that it's going to split like 30%. So first it finds a replication group which will be handling this table. If there is no appropriate replication group, then it can create a new replication group based on the available pool of nodes. So let's suppose that the replication group 2 is the one which is going to handle some part of this talks table. So first thing, we set up this replication group, tell that be prepared to take some range of stocks table. And then next it does is it updates the metadata manager, and at the same time tell the replication group 1 that, hey buddy, do not take any writes for stocks in certain range. So let's suppose that we decide that for stocks table A to C is going to go into replication group 2 and C till the end will go into replication group 1. So it's going to update this information in the metadata manager, so request manager, and eventually that information will reach request manager. At the same time, the controller is going to tell replication group 1 that, hey, do not take any put request for this range of stocks table. So if it does get a put, it will redirect that to the replication group 2. So request manager, all the request manager will eventually know that replication group 2 is responsible for this stocks table. The request manager who don't know that will talk to replication group 1, and replication group 1 will reject that request, the put request, and say that, hey, you talk to replication group 2. So at certain interval of time, let's say T1, we will completely cut over the put into replication group 2, where the range A till C, not including C, is going to replication group 2, and range C to end is going into replication group 1 for this table stocks. Next, let's see how we'll handle gets. Once we cut over the put, the controller will also start copying the A till not including C data from replication group 1 into replication group 2. But the gets might continue to come for this stocks table, and at this point what we're going to do is a dual read. So if a request comes from range C till the end, then we know that there is no ambiguity around that, and that request will only go to replication group 1. But while the split is still in progress, if a request comes for stocks table in range A to C, then request manager via metadata manager knows that this part is still under split or still under migration from replication group to replication group 1 to 2. So it's going to make a dual request. It's going to make a request to this guy, it's going to make a request to this guy. And it's going to get a data from both the guys. If the data is present in both the places, then it's going to use the sequence number to compare and see which one of the higher sequence number should win, and then return that data back to the requester. Similarly, the list operation will work in the same way. If someone says that, hey, give me a list of all the items in stock, when the request manager is talking between A to C, it knows that this part is under split, so it's going to talk to both replication group 1 and 2, and then get the data from both the places and merge those data based on the sequence number and return the result back to the client. After controller is done copying all the data from replication group 1 into replication group 2, at that point the copy is complete, and then we can completely cut over the read into just replication group 2. So after the copy is complete, we'll remove this special marker on this range, and then all the gets will just go into replication group 1 for range A to C, and all the gets will from C to N will continue to go to replication group 1. Again, there are a bunch of race conditions here, and we're going to talk about that next. Let's talk about the situation where we have two leaders in a replication group. So as I said before, leaders and all the followers are constantly heartbeating with the metadata manager. If a leader does not heartbeat for, let's say, 1 second, metadata manager will go ahead and elect another replica which is in sync with the leader as the new leader. So let's suppose it elected this guy as a new leader. But that doesn't mean that this guy will automatically stop acting as a leader. Most of the time it should know that I'm not a leader anymore, but there are some times it will not. So this is how we protect against two-leader or split brains. When a new leader is elected by the metadata manager, the first thing it's going to do is going to talk to the majority of the replication nodes and make sure that majority of them accept this guy as a new leader. So it's going to tell this guy and this guy that, hey, I am the new leader, accept me as a new leader. And as long as majority of them said, yes, we accept you as a new leader, then only it'll go ahead and take the new leader position. So let's suppose that this leader is still in its own world because of network partition or something, and the old leader is still thinking it's a leader, and the new leader got a confirmation from this node that, hey, yes, you can be the new leader. So this guy is now following this guy rather than this leader. So now when the put comes, and when a put would accidentally land up on this guy, on this old leader, because the metadata information has not propagated to all the request managers, this guy will then try to talk to the majority of nodes and try to do the put. At that time, those nodes will come out and say that, hey, you're not the leader, so we are not going to accept put through you. And then this guy cannot finish that put, which means that it cannot do anything about it. If a put comes to the new leader, it will try to talk to the majority. This guy knows that this is the new leader, so it's going to accept the put from here. And then this new leader will respond success to the request manager, and it can respond success to the client. So the deal here is that the followers will only accept the put request from they think who the leader is, and we only elect a new leader when that leader can confirm with the majority of the nodes that they agree that it is a new leader. So this way we never have a consistency problem because of two leaders, because even if you have two leaders, majority of them accept one guy as a new leader, and as long as that's happening, we will never be in a place where old leader might accidentally commit some data which is not committed in the new leader. Same, which is not committed in the majority of the nodes. Same will happen in the get path. If a get goes to an old leader will try to talk to all the nodes, make sure that it's still the leader. They will say that no, you're not the leader, so this guy will reject that get request. And if a get went to the new leader, it'll again talk to the majority. This guy will say that you are the new leader, and this guy will then respond to that get. So we dealt with two leader or split brain situation. Next is no leader situation. Let's suppose the leader fails for some reason. Then for 1 full second or whatever time is configured, metadata manager will not elect a new leader, and for that duration of time the entire replication group is unavailable. So again, this is a availability problem, not a durability problem, not a consistency problem. And obviously we want our system to be as available as possible, but it's still not as bad as, say, for example, losing data. To improve on this situation, there are a couple of things we can do. First is we can be more aggressive in between leader and metadata manager. So instead of 1 second, let's say if a leader does not heartbeat in, let's say, 500 milliseconds, then the metadata manager tries to elect a new leader. Another thing we can do is controller keeping a deep check on the leader and making sure that all the stats about this leader's host or nodes is up to date, it's correct, is in good health. So if we do have a bad leader, let's say once in a 15 days, and we have an outage of 1 second in once in 15 days in one replication group, I think it's an acceptable situation. What is not acceptable is a failure every hour or every 2 hours in a replication group. Let's check box no leader problem. The next two problems are of same kind, where we can have a network split at a metadata manager or outdated table metadata at request manager. So we did not go into too much detail into the metadata manager, but it itself consists of 5, 7 or even 9 nodes. For example, if you see the configuration, how Zookeeper is configured. In here also there is usually one leader, and it works through consensus protocol which goes through the majority of the nodes. So what can happen at metadata manager is a network split. So let's suppose that these three nodes go into one network and these two nodes are in the minority network and leader is on the majority side. So if a new change happens as a metadata manager, for example, a new leader is elected in a replication group, or a table is split over multiple replication groups, then that information will propagate to the majority side, but will not propagate to the minority side because there is a network split. Also, what happens here is that RM2 or request manager 2 will get that information, but request manager 1, which is in constant touch with just this guy, will not get that information. So request manager 1 will work with an outdated metadata information, and then it will go and talk to the replication group. But here we have a protection. The replication group itself will reject the request if it feels that it's not coming to the right node. So for example, as we looked before, if we try to make a request to the replication group 1, and if it thinks that it's not the owner of that particular part of the table, then it's going to tell the request manager that, hey buddy, I'm not the owner, your information is outdated. At that point, request manager will know that something is wrong here, and it will try to establish a new connection preferably on the majority side, and then it will fetch all the new metadata information, and then its in-memory state will accordingly be updated. Let's checkbox these 2 points. So the next point, if the node goes down before updating B+3 or LSM3. So if you remember from before, first we append the data to the append-only log, and then we apply that into the B+3 or LSM3. If before applying to the B+3 or LSM3 the node goes down, then it's okay because we can replay the logs from the append-only logs, because the append-only logs has flushed that data into the hard drive, guaranteed. So we can replay those logs back and build this B+3 or LSM3. So let's check this box. What if we have a bad request manager? If you have a bad request manager, and if it's, let's suppose it has some incorrect metadata information, it's okay, because when it goes and talks to the replication group knows that all the nodes in replication group operate by majority, and it will certainly reject that request from the request manager. The next thing is bad replication group node. It's possible that one node in a replication group is not behaving correctly, and that's also okay because inside a replication group we are always operating by majority. So even if one node is not behaving correctly, as long as majority of them are behaving correctly, we are in a good state. If majority of them start behaving incorrectly, then we are in trouble, but hopefully we can avoid that by a good checks on the controller and bunch of other things. And the final thing is multiple node failures in a replication group. Again, if you have multiple node failures in a replication group, it's an availability problem, not a consistency problem. It could be a durability problem if we lost all the 3 nodes. But hopefully it will never come to that situation. One way to avoid that is to have 5 node replication group instead of 3 node replication group. Other thing could be deep checks by the controller on all the nodes and make sure they are in the good health. So these are some of the race conditions which I wanted to talk to you about for this design. Next, let's talk about the scale, or how much data our database can handle. We can assume that every node in our replication group has a 5 terabyte capacity where we can run 5 or 6 disks of 1 terabyte each. Since all the nodes have exact same data, then we can say that replication group capacity of storing unique data is 5 terabytes. If you run 100 replication group, that's like storing 5 petabytes of data, and that should be more than enough for most of the reasonably large use cases. If this is not enough, then you can run 10,000 replication group, and that's like 50 petabytes of data, and that's a lot of data capacity storage. Limit on key value, you should always limit that, and we could assume a limit of 1 megabyte, and you should not allow key value more than 1 megabyte. If you have a use case to store that, then you should consider storing them on blob storage instead of a system like this. Also, most of average cases should have a key value size of 100, 200, 300 bytes or even 1 kilobyte and not 1 megabyte. Overhead per key value should be about 30 bytes, where 16 bytes was a sequencer, and then we can have some 20-30 bytes for storing index data in LSM3 or B+3. I/O per application group could be up to 2000 per second. Metadata overhead per application group could be up to 30 bytes, where we store for which application group, what are the nodes and who is the leader and all that information. Metadata overhead per table could be also up to 30 bytes. We can assume that RAM on a request manager can be 16 gigabytes, and 4 gigabyte of that could just be used for storing metadata information. So given 4 gigabytes, you can try to figure out how many request replication groups and table information can be held in memory of a request manager, and based off that you can come with a total capacity, total storage capacity and total I/O capacity of your database system. So this is all I have to talk about how to design a large-scale database system. Obviously this is a very high-level overview, and I expect my viewers to go in and read more about this topic. Again, please comment on this video, share this video, like this video, and check out my Facebook page. Thanks again for watching this video.